Today, I'm helping out Robert Moss as he prepares for his data science interview. These interviews can be pretty daunting and challenging. I'm hoping this video will be beneficial to both practicing data scientists who just want to revisit some of the fundamentals, as well as people who are trying to crack into the field and prepare for their first interview. I hope you enjoy our discussion, so let's jump into it. Say you're building.
Okay, so we're talking about question number 5 in the ACE the Data Science Interview, Chapter 7, Machine Learning. Say you're running multiple linear regression and that you have reason to believe that several of your predictors are correlated. How will the results of the regression be affected if several are indeed correlated? And how would you deal with this problem? Yeah, so just kind of looking at this question, I would say that the correlation, the fact that multiple predictors are correlated violates one of the assumptions of linear regression, which is that
I can play devil's advocate and be like, well, so why?
Which is that all of the variables have to be independent of one another.
But why would you want to assume such a thing?
Why? That is a good question. You would want to assume such a thing. I mean, I want to say because of Gaussian statistics. Like just yeah.
So actually we had filmed a little bit, or we had talked a little bit, but then we didn't film it. So let's go back. So I have this example. So I choose a bunch of random numbers between 0 and 1. Doesn't really matter. And then here, we don't need this one. Let's actually just do this. So then I just repeat the first column, right? So I just repeat the figure. So and let's make sure we get that one fixed. And let's do x repeated dot shape. There we go. So you got 100 data points with 2 features, and the 2 features are literally the same. So if we look at the correlation, it's literally 1 on the off diagonal, which is as high as it can be. And then let's make the target variable just the first feature plus a little noise. So this is like the Gaussian random noise that you assume in linear regression. So then we fit our model, and then we look at the coefficients. So here's one thing I just kind of think of. So so first of all, the weight for each coefficient is evenly split, which is fine because of course they're the same feature. So as long as they add up to 1, it's going to be pretty much what you expect. So that's good. I guess one bad thing is that like really you should have 1 feature and the coefficient should be exactly 1, right? But here we have 2 features and the weights are 0.5. So if you were just like looking at your model and looking at the coefficients, you might naively think that like these features don't matter as much because it's only 0.5 as opposed to like 1. So like it actually how to put this? It like it shrinks the size of each coefficient because there's 2 of them.
So you don't realize how important it kind of like makes one feature less important and the other one more, because really you can get the same prediction with just 1 feature. And now it's saying you need both and you kind of need, 0.5 of each, but you could actually just get the same amount of information from 1 feature and none of the other one.
And this could be a serious, exactly. And this could be like a serious, let's put like a bunch of them. So there's 5 features here. Do the same thing. And like now the size of the coefficients are getting really small. So what if you had like, a bigger model of like, 1,000 features and 100 of them are correlated to each other? So that could, I could really shrink the coefficient. And sometimes the reason why this might be relevant is sometimes with linear regression, you kind of get rid of the features with, small, like a small like beta coefficient.
To focus more on the important features.
Exactly. So you might accidentally get rid of some important features just because it looks like the coefficients are small, but in reality, they're all part of a bigger picture where there is 1 feature that is, given a large coefficient.
I mean, kind of what I'm reminded of with this is that classic data set where with like car data, you get like wheelbase and car length and engine size and all that stuff. And a lot of those features are highly correlated because like obviously, you know, the size of the wheelbase is, you know, correlated to the length of the car and kind of stuff like that, or, you know, all of that stuff.
So you repeated to me. So what do we just kind of figure out?
Yeah, so it says how will the results of the regression be affected if several are indeed correlated? So I say it's going to minimize the importance of the correlated features because it's going to spread their beta coefficients over like a larger feature set.
Yeah.
Yeah.
I think that's quite reasonable. And then if they ask you to clarify, they might, but they might just be happy with that. Yeah, that's fine.
Yeah. And then how would I deal with this problem? I mean, there's two different ways you could go about it. Again, you could use like domain knowledge, like looking at the car example, you
All right,
know.
no domain knowledge. Let's think about.
Okay. So I would use a heat map. I would use a correlation heat map of the features. I would look at which features are correlated, and then I would remove highly correlated features.
Okay, so let's think about this in practice. So it turns out we have here, they're all correlated to each other. So how would you actually go about doing this?
If those ones are all, how would I go about doing that one if they're all correlated to each other?
Yeah.
Can you make a heat map of that?
I mean, the heat map's going to be. I can, but
Yeah.
is it necessary? Okay, we can. And
No,
the heat map's
no.
going to be constant color.
Oh, okay. Yeah. No, my fault.
So let's make it heat map with Seaborn. Let's see if this works. Yeah. Dark mode.
Wow, you don't even get the little squares. Yeah, it's just one constant
Constant,
color.
right? Yeah.
Yeah.
All like this one.
Yeah. So I mean, again, that's kind of a tough call because they're all 0.2. I mean, if it's one constant color like that, then I know I can shrink it down to one feature.
Okay, so you're I'll just tell you, you're kind of missing something. So correlation is something.
Because is it because they all have the same beta coefficients? If they're all the same beta coefficients of 0.2, 0.2, and there's 5 of them, I know I can take all the ones with 0.2 out.
No. So you can actually, without running your linear regression model, you can compute the correlation, right?
Yeah.
Like this is before we do the linear regression. We already have the correlation matrix and the heat map. So actually, you can think of removing correlated variables as like a pre-processing step before you do machine learning.
Yeah.
So therefore, we won't know the beta coefficients because we won't have trained a model yet.
Yeah.
So then that still leaves the question, well, how do I actually figure out how to remove, or I know some of these are highly correlated because look, it's constant.
Mm-hmm.
How do I actually go, like, what's like an algorithm for making sure I don't have any highly correlated features? And I can tell you might be a little confused, so I can just kind of tell you what's going on.
Yeah, no. I think I heard you can use logistic regression for that somewhere. I remember coming across it, but
maybe.
Yeah.
I think there's a simpler way.
Yeah.
So correlation is kind of like a statistic about basically two features.
Mm-hmm.
So if I give you two features, you can in like a data set, you can compute the correlation.
Yeah.
So how you can go about it is like however you order the features, you start with your first one and you kind of look and see, is it correlated to any of the other ones?
Yeah.
And you can do that. You can look at the heat map, but actually what you would really do is you would look at the correlation matrix itself. So you would look at this matrix and you would probably have to code because usually it's not 5 by 5, but usually it's like many dimensions. You'd have to like write a little script or a little cell in Jupyter Notebook to figure that one out.
Yeah.
But you could see like, hey, this correlation is high. So that means the first feature is highly correlated with the second feature.
Yeah.
So how do I get rid of, well, I could just literally get rid of the first feature, right?
Mm-hmm.
and then that would remove the two correlated variables.
Yeah.
Because I'd have the first feature, I would remove it, and I'd still have the second feature. So basically, if there's two features that are correlated, you just want to get rid of one of them.
Yes. Yeah.
Because that'll, like, as we saw, if we remove a feature, that'll still keep most of the information.
Yeah. And then we want to run it again. We just, we want to run again, see what our correlation, see what our correlation coefficients are again, and then continue.
Yeah, like without thinking about like efficiency of running the algorithm or anything.
Yeah.
You literally just go through column by column and you say, okay, is column 1 correlated to any of the other columns?
Mm-hmm.
If no, then I just save it, and that's going to be part of my final like data set, like this data set. And then if it is correlated, you remove it and you don't think about it again.
Mm-hmm.
And you go through this until you're done. I guess one minor technical thing is you're always correlated with yourself, so you'll have to, you have to make sure you're not. I've seen people make mistakes like that, but other than that, yeah.
Can you clarify?
You're
always correlated with yourself.
Yeah. So this along the diagonal, it's always going to be 1.
Oh yeah. Okay. Yes. Yeah.
So, but other than that, you just have to check and the reason why this is the way to go is because correlation is really a property of two features.
Yeah.
So you just check them pairwise. If it's not, if one feature is not correlated with any of the others, you keep it. Otherwise, you delete it and move on.
All right. Let's see what their official answer is.
I think they had one more question, or am I wrong? Oh, how would you deal with this problem?
I think we just covered that.
Oh, yeah, we did cover it. Let's see what they said. If we
So there'll be two primary problems when running a regression if several of the predictor variables are correlated. The first is that the coefficient estimates and signs will vary dramatically depending on what particular variables you include in the model. Yeah, I remember they talking about that. Like, again, when we added a bit of noise, you saw a lot of fluctuation in like those variable like coefficients, even though they should have been like 0.5 and 0.5. Like you added a little bit of noise to one and it became like 99 and like 1% to the other one. So, so it's hard to get a gauge on actually which variables are, like how they're properly weighted to the predictions. Yeah, so the coefficient estimates and signs will vary dramatically depending on what particular variables you include in the model. Certain coefficients may even have confidence intervals that include 0.
So we haven't really talked about confidence intervals, so we can skip that part. But yeah, that's something.
Yeah,
that's something.
I'm getting into them right now because I just busted out my Math for Data Sciences book. I'm on probability, to chapter 2 probability, chapter 3's in inference statistics. So we'll definitely be covering p-values and confidence intervals and stuff. So
that'll be something to keep in mind as you learn about p-values. Like why would correlated variables lead to confidence intervals that include 0? That's a good question to ponder as you learn that kind of stuff.
Yeah, well, yeah, and we'll definitely have to pick that up. Again, once we finish ML, we're gonna go back to chapters 5 and 6 and do stats and prob, and we're gonna focus on that stuff, which is good because right now with my professor for her like quant course, I'm writing some notebooks on probability distribution, so that's why I busted out the probability chapter today. Awesome. And we're starting going to like statistics and inferential like inferential statistics for like quant models and analyzing our quant models and stuff like that. So coefficient may even have confidence intervals that include 0, meaning it's difficult to tell whether an increase in the value at X is associated with an increase or decrease in Y or not. Hence, results will not be significant. The second is that resulting p-values will be misleading. For instance, an important variable might have a high p-value and so be deemed as statistically insignificant, even though it is actually important.
We were kind of seeing like a baby version of that with the coefficients being small.
Yeah.
But really, the precise way to go about that is what they're talking about through p-values.
Yeah, and again, it says it is if the effect of the correlated features were split between them, leading to uncertainty about which features are actually relevant to the model.
Mm-hmm.
Yeah, great. Really, really great kind of answer there. You can deal with this problem by either removing or combining the correlated predictors. To effectively remove one of the predictors, it's best to understand the causes of correlation. Did you include extremes such as 2x or some latent variables underlying one or more ones? You can include it or affect both. To combine speech predictors, it is possible to include interaction terms, the product of the two that are correlated. Additionally, you could also center the data and try to obtain a larger size of sample, thereby giving you narrow confidence intervals. Lastly, you can apply regularization methods such as bridge regression. Anything you want to clear up in that second chapter there? Sorry, in that second paragraph?
Did you get what they were saying by when they said, like, there's a lot going on here and we could cover it all, but I think one thing that's useful is they said, or are there some latent variables underlying one or more of the ones that you have included? Do you understand what they mean by that?
If there's some variable you could use instead of the two, like one that kind of encompasses the two variables, is what I take from that sentence.
Right. Yeah, like, have you heard this latent variable before? That's what
No.
basically I was getting at.
Yeah.
So latent variable is like there's a nice picture. Let me see if I can share. I am sharing my screen.
Yep.
Latent variable BAE. That's a nice picture as well, but we okay. That's two. It's not the one I was thinking of. The StatQuest guy.
Yeah. Bam.
But basically, like, suppose you were trying to analyze like a picture.
Yeah.
I mean, I'll just explain it to you so we don't have to worry about that one too much. Yeah, so suppose you're trying to, process an image, and it's like, you could think of like the pixels individually, which tends to not work too great all the time, at least if you don't do some tricks. But like, you could try to discover latent variables. So like, suppose like the picture might be like, the common example is like if you're doing like cats and dogs. Like a latent variable might be like whether or not you're a cat or whether or not you're a dog. So like the picture is going to depend a lot on this latent variable. This like this kind of like deeper, like this variable that kind of like describe like high level what's going on with the picture itself. So this is roughly like what a latent variable is. So like what they're saying is if you have two correlated variables, maybe there's some like underlying reason why they're correlated. Like I think you mentioned the car example before, so like, yeah, maybe that is a good example.
Yeah. So again, if like you have like wheelbase and axle size and like the size of the frame would be the latent variable because the size of the frame is what's going to dictate the axle size and the wheelbase. Like axle size and wheelbase are going to be correlated, but it's actually like the total frame of the car that's actually going to dictate those two variables, I would say.
Yep. So yeah, what you said before about using domain knowledge, I guess it can be helpful if you're so lucky as to have the domain knowledge.
Yeah, which a lot of times in our industry we're not.
Yeah, it can happen.
Yeah, because they're trying to get us to replace domain experts. Which really we just should be augmenting their expertise. I think that's the way to go about it.
Yeah, I mean the goal is to be able to find the latent variables on your own. Without having to. Like that's kind of part of like the appeal of neural networks is the hope that you can find these latent, like the model itself will find the latent variables and then you don't have to worry about it. Like hand feet, figure it out.
Yeah, no, I'm really looking to going through like the individual algos with you, like how we kind of did the notebook for the linear regression, logistic regression, like, I'm really looking forward to going through that, especially when I get this linear algebra and stuff like under my belt. And just kind of talking about all the kind of math that's underlying a lot of these questions and stuff.
But yeah, okay. So I just figured I'd mention the latent variable because that's kind of they come up a lot, like in the sense that I've seen that word, that phrase, come up a lot in machine learning, and
Yeah.
somewhat not always understood, I feel. So just kind of
Yeah.
but yeah, there's a lot going on there, but I think we can move on. I mean, there's definitely more we could understand there. We could maybe revisit that after we're comfortable with p-values and all that.
Yeah. And then when you talk about combining predictors, like you just multiply the two together to get their product. Like how would you combine predictors? To me, that seems a little risky. Like not, huh?
Yeah, I mean, it could be risky, right?
Yeah.
Especially if you don't know what you're doing.
Mm-hmm. Mm-hmm.
It wouldn't be my first choice. I'll just say that.
Yeah.
But that's all right.
Yeah.
Uh,
Okay. 7.6. Describe the motivation behind random forest. What are two ways in which random forests? Describe two ways in which they improve upon individual decision trees.
oh,
So
that's a
I
good
would say the
question.
motivation behind random forests is that individual decision trees tend to have very high variance. They tend to overfit because on a decision tree, you can get a leaf node for every single data point. The motivation behind random forest is to remove that variance. The two ways in which they improve upon decision trees is one, they use reset. What's the word? Oh, damn it! I just had it. They use bootstrapping with replacement, where they're going to take random
There's
data
a word
point.
for that.
Huh?
There's a word for that.
Bootstrapping with replacement.
Bootstrap aggregation, right? It's like
Bootstrap aggregation.
bagging.
Yeah. So yeah, the two ways are bootstrapping and bagging, right? So the first thing is like, so bootstrapping aggregation. The first with bootstrapping is they're going to take random, they're going to pick random instances from the data set, allowing to pick the same instance twice. And they're going to train different decision trees on those separately bootstrapped data sets. And then as the tree is being trained, they're going to train the trees on different features randomly. And that allows for the individual decision trees to not keep on being trained on the same important features at the top of the tree. So it allows them to get a better sense of the core of the features that are not the most important.
So if you had to isolate what was the most important thing and so suppose the question was to describe the motivation behind random forests.
Yeah.
What would be like the concise way you would answer that question?
The motivation behind random forests is that individual decision trees tend to have very high variance because they overfit their data.
Mm-hmm.
Yeah.
So then the random forest is a way of decreasing the variance.
Yeah, and creating a model that better generalizes to unseen data.
So I think almost less is more. So if you were going to answer just that question, I think you almost just say that, and then if someone want to hear more, that's great. Fine, yeah.
Yeah, and then I would talk
it.
So and then to kind of clarify the second part of the question, saying what are the two ways in which they improve upon the individual decision trees? The two ways, one would be bootstrapping with replacement, and then the other would be like what? Because I mean, to me, like bagging is when they combine all the results of the individual decision trees into one like prediction, right? Because they're bagging all, but the fact that it ran, I mean, to me, one of the most important facts, because I read about this over the past couple of days, kind of on both the interview kickstart and in this book material, is like they say like the big thing is that it trains it on random features, that each like individual decision tree is trained on a different subset of features, kind of like randomly. What is that process referred to kind of like technically? That's the bootstrapping. Is that part of bootstrapping?
Oh man, yeah. Maybe maybe I need to remember. I feel like bootstrapping is the one where it's like you're randomly taking a subset of your features.
Yeah.
And the aggregation is when you average over all the possible different choices. But let's actually You know.
Yeah. Okay. Okay. Here we go. Here's on page 99. It says two characteristics. This is literally verbatim. Two characteristics of random forest allow a reduction to overfitting and the correlation between the trees. The first is bagging, where individual decision trees are fitted following each bootstrap sample and then averaged afterwards. Bagging significantly reduces the variance of the random.
Wait. So what's bootstrapping?
Bootstrapping is sampling with replacement.
Okay, cool. So I actually had it right, but it's been a while since I had to remember that.
Yeah. And then yeah, because it says the first is because again, they teach like bootstrapping and bagging differently, but when they talk about it, like it's all rolled into one because they say the first is bagging, where individual decision trees are fitted following each bootstrap sample and then averaged afterwards. Bagging significantly reduces the variance of the random forest versus the variance of any individual decision trees. The second way random forest reduces overfitting is that a random subset of features is considered at each split.
Mm-hmm.
And that would be each split in the individual trees, preventing important features from always being present at the top of the individual trees.
Right.
Yeah. I mean, it's even hard for the authors of this book to like get stuff straight. Right.
But I think you kind of nailed that question, to be honest. I think also, which is great, but also random forests are like kind of like unfortunately, they're one of the easier models.
Yes. Yeah. But I mean, dude,
but great.
I gotta start somewhere.
Yeah, I agree.
Yeah.
Random forest is a good one. I still sometimes just use it as like a baseline just to see like, did I process my data right? Am I getting reasonable results?
Yeah, and one thing that I read about with random forest is they say it's used a lot in the industry because you can train it very fast and it's very good for like parallelization of your computations, right? It's very good on like distributed computers because when you're looking at say like gradient boosting class, like kind of trees, like kind of like when you look at boosting, you have to train the tree. You have to look at, you have to get your, normalized regression differences, and then add, kind of recalculate weights and then train the next tree. So it's like you're training trees sequentially, but with like random forest, you can train trees in like parallel and, in parallel.
I think with boosting, there's some tricks. So I wouldn't be so sure that it's not quick as well.
Yes. Yeah.
I think XGBoost is actually pretty quick.
Yeah. Well, I mean, in the interview Kickstart notes that I was doing, they said like XGBoost is like industry standard, like ML algorithm. I think like one of the guys that always wins the Kaggle competitions was just like, when in doubt, just XGBoost it.
It does work pretty well. Yeah. So
yeah.
But if I'm feeling lazy and I don't, random forest is it's like 3 lines of code. XGBoost isn't that hard either.
Yeah.
But XGBoost might be the hyperparameter tuning can be a bit more subtle, I guess.
Yeah. It's very highly optimized already. They're saying,
Okay, I wouldn't believe. It is. It usually work out of the box, but I wouldn't believe that it's highly optimized for any problem.
No. They were talking more like highly optimized as like an out of the box kind of algo because it's all like learning rates and kind of things.
Yeah, right. But if you really want best results, you'll have to play with it quite a bit.
Yeah. As I found out from that debit from that credit card set. Okay. Awesome.
So let's see. Let's just see quickly what they said, just to see if they have any idea that we miss.
Yeah.
Right, prone to overfitting. Yeah, and again, like a single decision tree might overfit because
overfitting. Not only can these.
So that's a good question. Why does a decision tree overfit? I think you kind of mentioned it in your answer, but let's go over it.
Yeah, decision trees can overfit because their depth can go so far down that you can get a leaf node for every data point.
You could, right, and a single decision tree.
Yeah.
If you have enough decisions, you could literally be dividing your training data into
your individual data points,
and then the variance would be huge.
Yeah,
agree with that, and then you can kind of, what if you don't take such a large depth? But you can imagine that there's kind of a spectrum that'll make the variance a bit larger.
Mm-hmm.
And that's one common thing. So if you have a model that's pretty good but it overfits, one common trick is to average over a bunch of these models. So that's kind of the random forest methodology.
Yeah.
They have the bootstrapping just as like a technical way to achieve this. That it's also good as well, but
Yeah.
averaging over the different models, that kind of work.
Yeah. So what are their bullet points here? So it says, as in other ensemble methods, using a large set of trees created in a resample of the data, bootstrap aggregation, right? So that's what they talked about there. Using only M less than P features at each split helps to, so that was we talked about with using a random subset of features at each split, avoiding
Really
very
easy to implement and fast to run. I talked about that.
Huh?
The next point was they're fairly easy to implement and fast to run, which is
Where's that?
third bullet point.
Oh, yeah.
Which is nice.
But that had nothing to do with the.
Well, it's a good reason to choose them.
Oh, yeah. That's weird. Yeah, no,
I mean, decision trees are even faster to run, but
yeah.
It is a weird.
Oh, yeah. Dude, this question's kind of weird. They kind of jump them before they're kind of answering bullet points that have nothing to do with the question. But yeah, they can produce very interpretable, results because of feature importance values, thereby improving model understandability and feature selection.
That's true, but it may be a bit beyond where we're at right now.
Yeah, and I would say that's more true for individual decision trees and not random forest.
Sorry?
I would say that's more true for individual decision trees and not random forest.
So the question is whether model understandability is, I mean, it's certainly better for decision trees, but what they're kind of alluding to is that you can actually make it kind of work for random forest if you, it's not like completely obvious that you should be able to, like, with one decision tree, you can literally walk through the decision tree and say, okay, this is why my model picked this exact prediction.
Yes. Yeah.
When you're averaging over two already, it's getting a little annoying because you have to check both of them.
Mm-hmm.
You can check both of them and check why.
Yeah.
So.
Yeah.
And then you can, when it's a lot of trees like you would in an actual random forest model, there are some tricks, but we don't have to get into the tricks.
Yeah. Yeah. And I'm sure there's some like out of the box algos that'll give you that stuff. All right, 7.7. Given a large data set of payment transactions, say we want to predict the likelihood of a given transaction being fraudulent.
Ooh, however, there are you're an expert at this.
Yeah, I know, right? However, there are many rows with missing values for various columns. How would you deal with this? I mean, this is very vague. I would like to know exactly how many missing rows I have, so how many rows have missing.
Yeah, you might say I would want more clarification, and then just chuck out some ideas that you might try.
Yeah. Again, you can always replace with the mean of the column. That seems to be like the go-to. Well, first of all, I wouldn't like to remove the rows because then you're moving a lot of, if you have a lot of missing values in a column, then you're removing a lot of the rows from your data, and that data is very hard to come by. So removing rows, I think, is just out of the question right off the bat. If it's less than 10% of your data and you got a lot of it, then yeah, just get rid of them. But if you're running like more than 10%, I would not get rid of that data. I would replace with the mean of the column.
So, do you know what that's called when you replace like missing value by the mean?
No, I don't.
That's like imputation.
Mean sample and imputation?
Imputation, or impute the data.
Yeah, so mean sample imputation? Or just imputation?
Yeah, it's a method of imputation. I don't know what the exact name for when you replace by the mean.
Yeah.
You can replace by mean, median. You can kind of decide how you would do it.
Yeah. I mean, I've seen, one thing I've seen with like people going at the Titanic data set very fancy ways is like, if they're missing ages, they'll, and they have other information, they're like, well, what's the average age if someone's a mister, right? And if someone's a mister, then they'll take the mean of like different subsets of different subsets of groups within the column, right? So you can do that to kind of get more finely toothed comb with it. But that's, given the information for this for this question, that's about all I would say about that question.
So there's a couple other things. So first of all, let me think. So first of all, you actually know for fraud. So what's kind of special about fraud data?
Highly skewed data sets.
So it's imbalanced, right?
Yeah.
So if it did happen to be the case that a lot of your missing data was from the non-fraud case, which would be the larger portion,
just get rid of them.
You could just get rid of them, right? It's probably,
yeah.
You would already have to do some sort of like oversampling or whatever it is.
Or undersampling on, yeah.
However, that could be, well, yeah, if it's non-fraud, that's probably okay. So that's one thing. Yeah, the other thing is, like you actually gave a good idea with like trying to use another feature, like if it's like to predict, to get a more
subgroups within the column. Yeah, to kind of calculate different means of different subgroups within the column. Yeah.
So that was good. Yeah. So
cool. Let's see what they say. I'm sure it'll be 3 paragraphs long.
I kind of quickly look. Yeah, that we kind of hit all the main points.
Yeah. Okay, yeah, so clarify the missing data. Since these types of problems are generally context dependent, it's best to start your answer with clarifying questions. For example, is the amount of missing values uniform by feature, right? Are the missing values numerical or categorical?
That's actually important, the numerical or categorical, because you wouldn't want to use the mean if they're categorical.
Yes. Yeah, so let's talk about that. So if they are categorical, what are you using the most?
You can just use the most popular, the most popular class as
yeah.
This is all as a starting point. Like you'd have to see model performance and then kind of judge. Make a judgment call from there.
And then how many features with missing data are there? Is the pattern and the types of transactions you have a lot of missing data? But also used to think about why the data is missing, because it affects how you impute the data. Missing data is commonly classified as missing completely at random, missing at random, not missing at random.
So what they're kind of saying is there's not really a one size fits all. Which is why, like, chucking out a few ideas and saying, maybe even saying that there's not really a one size fits all. You kind of have to see what your data kind of tell you to do, basically, or what makes sense.
Yeah, again, this answer is like the entire page, but like step 2, establish a baseline, which is what you hit on, which was what if the missing data is in transactions that were almost never fraud, right? So what if the missing data is mostly in columns of whose features don't have good predictive value, right? So that's also good stuff too. Impugn missing data, which is what we talked about. If the baseline model indicates they're dealing with missing data that is worth it, one technique to be is used as imputation, right? Check performance with imputed data. So use model features. With these models, you can run the set of classification algorithms to predict fraud or non-fraud. With this imputation technique, we can also cross-validate to check whether performance is increased by including the impugned data, right? So we'd want to just check it with running without the impugned data than with the impugned data. So if we were running the model without the impugned data, we would just not use the rows. We would have to take our data set and take the rows out, correct?
If you just remove the rows with the missing data, you can do that.
Well, it says check performance with imputed data. With this imputation technique, we can also cross-validate to check whether performance increased by including the impugned data relative to just the original set.
Yeah, exactly.
So if we were running the original set, we would have to remove the rows with missing values.
Right.
Yeah. Finally, thinking outside the box, is it possible to use a third-party data set? Oh yeah, that's a good one. Third-party data set to fill in some of the missing information. Suppose a common missing piece of information was the type of the business that person paid. Yeah. Okay.
So in conclusion, you have missing data and you want to just find some sort of methodical way to predict what your best guess can really be for that missing data, whatever that methodical way may be. We have some techniques, imputation, remove the rows. You might even remove it and not even worry about it.
Yeah. Feature importance. Is this feature important? It's
Oh, you're talking about removing a column.
yeah.
Which maybe, yeah, you could maybe do it. So yeah, you sound like you're. I would be hard to say. Sounds like you're understanding that kind of thing.
Yeah, I
I mean,
sound like a data scientist. Given a bunch of different ways you could go at it. Situationally dependent, right?
yeah, I mean, it's not like the random forest question where there is really like kind of one right answer. Like, why do you
Yeah.
use random forest over decision tree? Well, it's because it kind of decreased the variance. That's
Yeah.
basically the main reason.
All
All right, I
right.
think we could call it here.
Yeah.
So yeah, let's call it. Yeah, that's good. Good session.
You don't want to do one more?